We have finally reached the point where a quantum computer becomes more reliable as it gets larger, which is a result that completely contradicts the way we build every other machine on Earth. How did a grid of fragile physical parts manage to create a single virtual state that is more stable than any individual piece used to build it? In this video, we will answer the question of how quantum error correction finally crossed the threshold and what this means for the future of computation. By the end of this episode, you will understand exactly how the Willow generation hardware proved that we can now suppress errors faster than we create them. The core spark of this discovery is a visible clue in the data where increasing the number of qubits from 25 to 49 caused the failure rate to drop instead of climb. We know that individual quantum bits are incredibly fragile, but it was unclear if we could ever stack enough of them together to outrun the noise they generate. This result confirms that the mathematical threshold theorem is a physical reality, and it changes our understanding of these machines from experimental toys into stable engineering systems. Traditionally, we thought that adding more parts to a complex system always created more points of failure. But in the quantum world, we have just proven the opposite is true. The default story of quantum computing, for the last 30 years, has been one of constant struggle against the environment. Scientists told us that qubits are like delicate glass spheres that shatter if a single stray photon or a tiny increase in temperature touches them. In this old model, the goal was simply to make the individual spheres stronger or the room colder to keep the information alive for a few more microseconds. This approach reached a ceiling because you can only isolate a system so much before you lose the ability to talk to it. The contradiction that researchers kept hitting was a phenomenon called the negative scaling trap. Every time someone tried to add more qubits to a processor to do a bigger calculation, the total noise in the system grew so fast that the computer became less useful than a smaller one. It seemed like there was a natural limit to how big a quantum machine could ever be, because the errors would always pile up faster than the processing power. This led many skeptics to believe that large-scale quantum computers were a physical impossibility, regardless of how much money was spent on them. To understand why this problem was so difficult, we have to look at the microscopic chaos inside a quantum chip. A single physical qubit usually loses its information in about 100 microseconds, which is roughly the time it takes for light to travel 30 kilometers. If you want to perform a long calculation, you need the information to stay stable for seconds or even minutes, not tiny fractions of a blink. The old model predicted that if you tried to link these qubits together, the interference between them would cause a chain reaction of mistakes. However, the latest measurements from the Willow chip show a strange result that breaks this prediction. By arranging the qubits in a specific checkerboard pattern, the researchers found that they could identify and fix errors without ever looking at the data itself. This is the first anchor contradiction to the old belief that more qubits equals more failure. When the team moved from a smaller grid to a larger one, the logical error rate fell by a factor of more than 2. This measurement is the proof that we have moved from the era of noisy hardware into the era of active error suppression. This breakthrough works through a mechanism called a surface code, which is a way of spreading one piece of information across many different physical points. Instead of trying to make one perfect qubit, the researchers created a logical qubit, which is a virtual entity that lives in the correlations between dozens of physical neighbors. Think of it like a group of people holding hands to form a circle. Even if one person lets go, the circle remains a circle because the others are still connected. The significance of this is that the information no longer has a single physical location where it can be destroyed. The process uses a technique called syndrome extraction, where dedicated check qubits perform constant background measurements. These checks do not look at the value of the data, which would collapse the quantum state, but instead they look at the parity, or how the qubits relate to one another. This allows the system to see that a mistake happened without destroying the calculation in progress. This micro-reframe changes how we view quantum memory because it turns a static storage problem into a dynamic process of constant repair. One of the most impressive parts of this measurement is the real-time decoding requirement. For error correction to work, a classical computer must sit next to the quantum chip and process gigabytes of error data every second. It has to identify exactly which qubit flipped and tell the system how to compensate for it in less than a millionth of a second. If the classical computer is too slow, the errors pile up into a mountain of noise that no algorithm can fix. The Willow experiment proved that this loop can be closed at a scale that was previously thought to be impossible. The data shows that the logical state can stay alive for much longer than any of the physical parts used to build it. This is a profound shift because it means the machine is now more stable than its components. It is a reality check for the skeptics who argue that the overhead of error correction would always be too heavy for the hardware to handle. We now have a clear signal that the more we scale the grid, the more the errors are suppressed. To see this pattern clearly, we have to look at the difference between distance 5 and distance 7 memories. In the language of quantum codes, distance refers to how many physical errors it takes to actually flip the logical bit of information. A distance 5 code can handle a few mistakes, but a distance 7 code is much more robust because it requires a larger chain of failures to break the logic. When the researchers increased the code distance, the logical error rate dropped exponentially. This is exactly what the threshold theorem predicted back in the 1990s, but it had never been seen in a real physical system until now. The old model suggested that the crosstalk between qubits and the noise from the measurement process would ruin the scaling, but the evidence shows a clean downward slope. This measurement logic confirms that there is no hidden physical law preventing us from building a massive quantum computer. The success is not just a single correct output, but a statistical pattern that proves the system is under control. This brings us to a major challenge known as the classical audit wall. As these quantum grids get larger and more efficient at correcting themselves, we reach a point where a classical supercomputer cannot simulate the state to check if it is correct. We are entering a territory where the quantum machine is the only thing that can verify the quantum machine. This creates a missing signal problem for traditional verification protocols. How do we trust a result that no other computer on Earth can double-check? The answer lies in the error curves themselves. By showing that the error rate drops predictably as we add more qubits, we create a chain of evidence that the machine is functioning as intended. We are moving away from needing to see every step of the math and toward a model of statistical verification. This changes the viewer's understanding of proof in physics because it shifts from deterministic certainty to a high-probability map of success based on threshold behavior. There is also the problem of cosmic rays and high-energy particles that can interfere with the chip. Even if the internal noise is low, a single particle from space hitting the processor can cause a burst of errors across many qubits at once. This was a major concern for the stability of logical qubits because error correction codes are usually designed to handle one mistake at a time, not a whole neighborhood of them. However, the Willow generation hardware showed that the surface code geometry is surprisingly resilient to these events. The system can identify the cluster of errors and isolate them, preventing a total collapse of the logical state. This is a concrete trace of the system's robustness. It proves that the engineering can handle external environmental shocks that were once thought to be deal breakers. Every time we find a new source of noise and show that the error rate still follows the downward threshold curve, the case for large-scale quantum computing becomes stronger. Most people do not know about this breakthrough because the results are hidden behind complex statistical graphs rather than a single flashy headline like a new rocket launch. There is a hidden mechanism gap where the public sees quantum computing as a mystery, while the engineers see it as a very specific problem of signal processing and error rates. The reason for this gap is partly due to the missing records of how these machines actually fail. For a long time, companies only reported their best results and ignored the messy data of error cycles. But the Willow results are different because they show the full picture of the machine fighting against its own noise. This transparency is what allows us to see the threshold being crossed. It is not about reaching perfection. It is about reaching a point where the math of the code is stronger than the physics of the noise. This realization shifts the focus from finding the perfect material to finding the most efficient way to run the error correction loop. When we look at the parity checks, we are essentially looking at the eyes of the machine. These checks are performed by ancilla qubits, which are extra parts that act as observers. They entangle with the data qubits to see if a flip occurred, but they do so in a way that respects the no-cloning theorem of quantum mechanics. You cannot copy quantum information to make a backup, so you have to use this decentralized memory approach, where the information is stored in the relationship between parts. This is a fundamental limit of physics, that the surface code turns into an advantage. By using these ancilla qubits to monitor the system thousands of times per second, the researchers have created a continuous correction cycle. The result is a virtual stability that outlives the physical life of the hardware. This is the mechanism that allows the machine to cross the line that classical checks cannot follow, as the complexity of the entanglement grows far beyond what a normal processor can map. Now we must answer the title question directly. How did quantum error correction cross the line that classical checks cannot follow? The evidence from the Willow generation hardware eliminates the old explanation that adding more qubits would always lead to more noise and eventual failure. The measurement of the distance 7 code proves that increasing the system size now reduces the logical error rate. This result has no account in the old model of linear noise growth. The mechanism that is strongest is the surface code operating below the threshold, where the rate of error suppression exceeds the rate of error introduction. While we still have unresolved questions about how this will scale to millions of qubits, the evidence forces the conclusion that the threshold barrier has been broken. The interpretation remains open as to how we will perform the final verification of results. Once we pass the limits of classical simulation, but the path to a stable, large-scale quantum computer is now a matter of engineering rather than a question of basic physics. This verdict changes everything for our understanding of the quantum world. We no longer have to view these machines as fragile and temporary. Instead, we can see them as the first examples of a new kind of matter, where information is preserved through a collective process of constant observation and repair. It is a transition from a world of passive isolation to a world of active control. For the viewer, this means the era of quantum physics as a series of strange, one-off experiments is over. We have entered the age of the quantum system, where the whole is truly greater than the sum of its parts. The forensic intrigue of watching these error rates drop as the machine grows provides a clarity that was missing for decades. We are witnessing the birth of a machine that can correct its own flaws faster than the universe can create them. This is not just a faster computer. It is a fundamentally different way of interacting with the fabric of reality. As we look forward, the stakes could not be higher. If we can continue to follow this downward curve of error rates, we will eventually reach the point where we can simulate the most complex molecules in nature or break the codes that protect all modern communication. The threshold crossing is the first step toward that future, providing a concrete signal in the noise that we are on the right track. Even though the classical world may struggle to keep up with the verification, the internal logic of the quantum machine is now undeniable. We invite you to stay tuned as we continue to track these anomalies and breakthroughs at the edge of physics. If you want to see more deep dives into the data coming out of the largest experiments in the world, consider following the channel for our next update on the frontier of human knowledge.